Okay, so we're going to be tackling one of the very sad APIs that exists out there. Why? Because Avro is a very good standard in terms of how to persist data in a more durable, efficient, in terms of binary representation, and also durable in the terms of schema evolution with the handling of compatibility issues. That's to say that with Avro you will be able to define a schema, makes it evolve through time. If you follow certain rules, you will be able to read all the data with a new schema and vice versa. But in terms of API, it's kind of painful to use. And that's the goal of this session, to make you create pain. You're going to be creating an algebra, or co-algebra, you'll see. Yeah. That will allow you to project the informations we have in our schema F pattern functor into an Avro schema. The Avro schema has exactly the same kind of construct that we have defined. That's to say an array type, a struct type, and some simple values. You've got also unions and things like that in the Avro specification, but we won't be tackling those because they add additional levels of complexity. At the same time, we already talked about that, but I emphasize once again that we are not going to be tackling the issue of nullability or optional fields, in other words. Okay? That's once again a bonus that you can handle afterwards. So you've got a single type, which is called schema, org.apache.avro.schema. And on this interface, you have a lot of methods. And 80% of those, in any given case, will give you an exception if you try to use it. Yeah. So when you're going to construct a struct, you will construct a schema. When you're going to construct an array, you will construct a schema, etc., etc. There is no other instance than schema. But you can know the kind of schema that you're using the getType method. The getType method will I see the disgusted faces of a lot of people right now, and that's very funny to watch. You've got a getType method that will give you a string and will allow you to know that you're having to deal with a record or with an array or a simple value like an int or string, etc. When you have a record, once again, you always have just one type, which is called schema. But if that instance is a record, then you can call the getFields method. You can always call the getFields methods, but this time it will work. And in the case of an array, you can get the element type. The cardinality of what we defined in our schema F are respected. That's to say that the getFields will be a list of something. Not exactly a list, but an array or an array list. And the getElementType type will be a single value, which is a schema as well. Okay? So that's to inspect Avro schemas. Okay? But for building them, you will have three options. For simple types, it will be easy. You will just have to use the schema.create with the kind of type, the kind of simple type that you want to create, with schema.type.int, long, etc. But for some simple types, which are not so simple, like dates, timestamps, they don't have their exactly, they don't really have a representation in Avro directly. They are what Avro calls logical types. That's to say that when you deserialize them, you will have a java.util.date, for example, but their representation will be a long when it's persisted. So you will need to define, using the formalisms of logical types dot something, you will need to define what you want to use in terms of standard to persist a date or a timestamp. And the norms of Avro being just like norms but more complicated. For example, for dates, their recommendation is to use an int with the number of days from 1970. Number of days. And for timestamps, to use, well, the proper timestamp, like a long, but with the seconds between now and 1970. That's just a recommendation. You can do pretty much anything you want. For example, here, the examples that we use is to represent a date with using a long in terms of storage, but using logical types, timestamp millis, meaning that we expect to go up to the milliseconds. But this type of metadata is not going to be used by anyone but you. So, I'm sorry?
You just have long in there. Are you? I've actually hit long before, so I'm very curious. But is it like, is there no metadata in the Avro such that you know just milliseconds versus microseconds versus seconds?
Once again, these types don't have concrete implementations. Right. So in terms of data, you will see a long. But in terms of schema, you will know if there is a logical type or not. Yeah, if you check.
We forgot to write it in the previous section, but you have a method called get logical types that lets you inspect, when you get a schema, that you inspect if it has a logical type.
And it will fail if there's none.
Of course.
Of course. So when you've got when you're deserializing data, when you're handling, for example, longs, then you need to check or know beforehand that what you're seeing is really a long and not a timestamp that you should be deserializing. Okay? So that's to handle logical types. For arrays, we will be using, I wouldn't even call them syntactic sugar, because it's not that sugary. But we will be using schema builder for both records and array. They allow you to have like a builder-in pattern to create more easily generic records or generic arrays, which is fine. It's not perfect, but it does something. It does give you some kind of sense that you're not doing anything stupid. So, for example, a schema builder.array will only allow you to specify items, and the items method will accept the schema of the element type. Okay? And finally, for record, that's to say for a struct, Avro has a very, I would say, sad tendency to imagine that you're going to generate C class, or C struct, or C++ classes, or Java classes out of the Apache Avro schema. So everything that you're going to be using needs to be compatible with the field names acceptable by Java standards, or with names that should be acceptable as classes name. A record for Apache Avro will be just like a class, which is basically what a struct is anyway. Okay?
And this is where it becomes interesting to us, because since these records are meant to represent classes, it means that the names you give to them need to be unique. If you are building a big schema and you are putting into that schema two different objects that represent records but have the same name, you'll have an exception. And that's why it becomes interesting for us. Because so far in our schema, we have absolutely no information that helps us to find a unique name for our records.
Monsieur.
And that's why it becomes painful, but interesting.
Yeah, because there's the pain of the API, and now you've got additional constraints that the schema F didn't have. So you need to generate names, and you need to generate them in a unique way and deterministic, because you want always the same Avro schema for the same schema F.
So to sum up the problem with these Avro schemas, we need to find a way to generate unique names for our records. And so there are basically two solutions, maybe more, but two solutions that come to mind. We won't be altering our pattern functor. It is sacred. We don't want to change it. But we can devise two solutions to come over that problem. Schemas are trees. And in a tree, each node has a unique path. So if we were able somehow to know the path of a node when we are projecting it onto an Avro schema, we can use that path, represented as a string, to build the name of the record. But remember, when with our algebras, we only care about one layer at a time, so we don't know where we are in the tree. So the first trick is to use a pattern from Matryoshka called env that allows us to decorate each node of a tree with some value, a value of some type E. So that's the first solution. And the second solution will be to use another technique to remember what record we've already built during our traversal and try to reuse this when we find the same structure. Right? So the comments should be almost enough to begin with. So maybe you can just start right away. And if you need to, we'll stop and explain the two different techniques in more detail. All right? Yep.
Is that Avro introduction available somewhere?
Unfortunately not, but I can push.
On the GitHub?
Yeah, I can push it on the GitHub.
So,
that's basically what we are trying to do. Right? With env, we are able to keep the same structure, but with a label on each node. And so then when we collapse our tree, we have access to the label. Right? So we can push information from the top to the bottom and then use that information back when destroying the tree. So you're talking about this one?
Yeah.
Yeah. So, of course, I've erased it. So, recursive type class allows us to forget about which fixed point we use, right? But we will still be using a fixed point, right? And the only characteristics of that fixed point that interest us is that we can extract or peel it off to get back a schema F. Okay?
Yes.
So all we need is to make sure that this type, T, is recursive with schema F. Which means we can extract a schema F out of that T. That's it. It's only that, right? But it allows us to, we could have written a specific version for fix of schema f, mu of schema f, nu of schema f, and so on and so forth. But the only thing we would have done with fix or mu or nu is just to extract one schema f out of that. Okay? Because, sorry? You use the project, it gives you the project method. You can do dot project on a t to get back a schema f of t. That's the only reason you need that type class. And we need that because we start from a fix of schema f, or a t of schema f, or a t in that case. And we want to walk through it to label each node. And in the end, we will get a fix of nth t of stuff like that. You see? But the only property that interests us about the type t is that we can extract a schema f of t out of it.
Okay. With this implicit, you won't have any issue with IDE IntelliJ.
Yeah, as a bonus.
It was, I mean, project is resolved.
Yeah. So recursive.aux gives you the project method. Co-recursive gives you the embed method that goes the other way around. And bi-recursive gives you both. So we will give you, yeah, maybe it needs a little bit more explanation. It's explained, but maybe too concisely. You'll start off with your T, which is your schema, along with an empty path. Because you still have to produce, to provide a path. You know, during, yes, because during the, you will, it's still an algebra, right? It's a classical algebra. So you will have this pair, path and T, throughout all the traversal, right? Because you will need it to accumulate paths. So you start off with an empty path, and that's it. Okay. One thing to note is that in terms of building the path, only the struct is interesting, because the path will be composed of the field names of the various layers of struct. Arrays and simple types, they have nothing to add to the path. So in that case, you will be able to write a generic case for all that is not a struct. So maybe this is the hint you needed. In the simple case where I'm not a struct, so I do not participate to the path. I just need to push it down. But to build my nth t, I need to put a tuple with a path and a schema f of tuple path t. But what I get here, in that x, is a schema f of t. So I have to map over that schema f to push down the path. So that's what I do. I map this schema f to produce a pair of the path and what was inside this schema f, which is a t. Right? And for the struct case, it's almost the same, but I have to use the names of the fields somehow to build up the path. It really helps to just follow the types here. What do I have? What do I need? How can I come up with a way to go from former to delater?
Arrow underscore shorthand for tuple?
It's a shorthand for that. Right? Which you can always write like so in Scala. That's the same thing. This arrow function, it builds a pair. Simply. Maybe I could have written it like so. I'm not sure. And it looks like Lisp.
So X is some like simple version of our schema F.
It's a schema F that isn't a struct. So it's an array. Yeah. It doesn't have anything that can participate to a path.
Because
you
for
see?
the array F, you don't have a field name.
You can't go down.
Yeah, that's it.
Got it. It's just a field.
Yep.
Does that make sense?
Yeah, so you're appending names to the existing path. Makes sense, right?
You do two things.
Yeah.
Because inside empty, well, we are bound to return an empty of labeled with path, comma t as the carrier, right? But our struct f of field, the case, is a schema f of t. So we have to map over it to push down the path, right? To transform the t inside the schema f into a pair of path t, right? That's why we map this. And we use that to push down, to build up the path using the field name. So we don't just produce pairs path and schema, but path plus the name of the field. And that's how the path is built up while going down.
So we're still not in Avro land, right?
Not yet.
You just labeled the tree.
Yeah, we are preparing ourselves to produce Avro schemas.
And this part can be used for many, many applications. This is not only about Avro. I mean, if you want to localize a field, a specific field, you could pattern match just on the path to just output the value, and that's it. That's another example of how you can reuse this part.
The empty technique. You can also use it to somehow traverse two trees in the same time. You label each node of one tree with the corresponding trees, subtrees of the other one, and so on and so forth.
You know every path going down from that specific node.
Yeah, but you can have any kind of label, not only the path. You can say, I can label each node of my tree with its depth, for example, or with anything else. Right?
You're basically creating a recursive zip.
Yeah, that's it.
Recursive zip, right.
The thing to note there is that we want to build path, and path starts at the root. So we definitely need to use a coalgebra, because coalgebra starts from the root and goes to the bottom.
Yeah.
Right? Yeah. So this is this kind of reasoning that you need to be able to form when working with recursion schemes. I have a problem. My solution is to label each node with its path. Path starts from the root, so I have to do ANA and a coalgebra. If you are able to work that way, it will be quite easy. But it comes with a lot of pain and hard work.